Thank you very much. Thank you for the invitation to speak to you today. I am permitting myself to speak in German. I have decided to not expose you to my English in a presentation. My topic are the potentials of industrial waste heat. And for the province of Vorarlberg, I had the honor of drawing up a study for potential clients in the Vorarlberg industry. This is going to be the primary focus of my presentation. To put all this in the context of energy politics, I'm going to start with a work that I conducted 3 years ago for a group of industrial players in Vorarlberg who really wanted to dive deeper and call Vorarlberg a Green Deal model region to see how the province could develop into a completely climate neutral region until 2030. This was the goal at the time. We modeled the entire energy supply for the year 2040 through a range of measures, a range of initiatives and strategies. And the result was that there should be a dynamic energy flow diagram, which I would have liked to show you as a video. Unfortunately, technology is not on our side today, so I can only show you the initial and the final picture. What you can see here is the energy flow diagram for Vorarlberg. I think you can see the cursor here on the screen. We import a lot of oil products, as all the Austrian regions do, really. They are used for fuel, for heating. We use natural gas for industrial applications. In particular, we have biogenic fuels, also split logs, wood that is being burned, also hydrogen. On the electrical side, just like Tyrol, there is a lot of hydropower also in Vorarlberg. So the electrical energy supply is covered by 75% by hydropower. The remaining 25% are largely imported. What we can see here, we are moving towards mobility here. Cars, there's not much electrical products here. Process heat, this is usually gas-based. I'm going to talk about this in greater detail later on in my presentation about this process heat and what we see here in terms of exhaust heat. Quite a small part that is used for heating networks, for space heating, about 4,000 gigawatt hours in Vorarlberg that are used for heating buildings, oil heatings, gas heatings, biomass. Not a lot of heat pumps, yes, electrical energy, all this is part of what you see here. So this is the status quo, the starting scenario. We have conducted several modeling processes to see where we could possibly go. I can only show you the final picture here. If we implement all these measures consistently, then we would like to achieve a climate neutrality, moving away from gas and oil with an entirely electricity-based mobility sector. You can see here the building heat is strongly reduced. Also in terms of efficiency, this is based on a dedicated strategy. What you can see here is also that the district heating share has increased quite strongly, although the heat demand has actually gone down. We were able to increase district heating from 300 to 1,000 gigawatt hours. So this is my topic today, district heating. This is not just based on biomass, as it was the case so far, or still is the case in Vorarlberg, but we also have a large share from large-scale heat pumps. And these large heat pumps are largely based on industrial exhaust heat. And I was commissioned with drawing up a study on this topic. And this is what I'm going to be talking about today. What is our status quo in Vorarlberg? We have 13 companies that participated in this study, and they stand for about half of the industrial gas use in Vorarlberg. So what industries are they, and what companies, what areas are these companies active in? We don't have any heavy industry in Vorarlberg, just like Tyrol doesn't. We don't have a steel industry, for example, or a plastics industry. There are no smelting processes that need extraordinarily high temperatures. We have mechanical engineering businesses, yes. We have quite a large food industry sector. some textiles, a fairly large paper mill, and the rest consists of smaller segments. What we looked at were 5 mechanical engineering companies, so from the largest sector, then several players, 4 players to be precise, from the food industry, 1 textile company, 3 paper industries, and several companies from the remaining segment. What you can see here is that the final energy consumption for these players varies greatly depending on the industry that they work in. For mechanical engineering, you don't actually need a lot of natural gas because you don't need a lot of process heat. But you do need a lot of electricity in order to keep the pumps and the motors going. For the food industry, the share of natural gas, that is heat, is of course higher because you're baking, you're cooking things, which requires heat. So we have very different demands here, and we have an inclination to say, well, mechanical engineering, we don't need a lot of heat, so we don't produce a lot of exhaust heat. That is not true, because electrical energy is also converted into heat in the production hall and is available as some sort of exhaust heat. For all these businesses, we compiled these sort of energy flow diagrams, just roughly showing the situation, but the idea behind it was to give an overview of the most important key factors. This is, for example, somebody from the plastics industry, where only electrical energy is used, although the plastics actually have to be melted at temperatures above 100 degrees. This is all done electrically in this particular business. So the electrical energy is used for different production machines, pressurized air, the drying facilities, and so on. And as you can see, the energy flows here on the right-hand side. You can see what actually leaves the building without being utilized at all. So what actually leaves the building via infiltration or transmission can never be used as exhaust heat. The products that are being heated and that are also transported in a warm condition and leave the building in a warm condition. Anything else that leaves up here, we see the potential here for exhaust heat. So these are energy flows that leave the building, for example, the exhaust heat from the cooling facilities. This refers to the free cooling, where machines have temperatures from 45 to 32 degrees. So this is a fairly high temperature level that you are always able to get via outside air, and the ventilation facilities that usually run with about 25 to 30 degrees. And the same applies here. We could actually apply the heat recovery principle to these as well. Free cooling is used when exhaust heat temperatures are higher than the outdoor temperatures. Exhaust air is what we call it. You could also call it outgoing air. The outgoing air is also the air that leaves the building, and the exhaust air is the air that is being suctioned out of the building. What we see here is the paper industry. So you can see the heat flows are quite strong here, 20, 30, 60, 70 degrees. These are all heat flows that are part of a heat network that works with 80, 90 degrees, and that are not being utilized directly. However, they are strong energy flows with several hundred gigawatt hours per year. This is has an enormous potential, and this energy can only be leveraged by using heat pumps, and this is what I'm going to be talking about in a minute. Another example, this is from the packaging industry. You can see lots of heat flows here, exhaust heat flows, and you can see quite well that the flows that can be utilized directly, so anything above 80 degrees, that would be flue gas, for instance, with up to 240 degrees from a post-combustion facility that is being used in a heat network already at this point. Everything else, unfortunately, is going to waste and is not being utilized. But what you can see is that the heat flows make up several gigawatt hours. In total, we have 10 here that are not being utilized, but that could be utilized in a way that makes sense for the business. So the ratio is about 1 to 10 between heat that can be used directly and heat that can be used indirectly. And that is really the decisive factor in the question of how much exhaust heat exactly do we have available. With these temperatures that cannot be utilized directly, we're talking about anenergetic flows. So this is energy that cannot be utilized directly, but needs some sort of temperature stroke. What did we find out about these sources of exhaust heat? For all the businesses that we looked at, we found out that the largest amount, more than 160 gigawatt hours, is available as exhaust air from the production processes, from fryers all the way to paper mills to printing presses. So this refers to air that leaves the building, contains emissions, but also a lot of heat. The colors of the individual categories show us the temperature ranges. You can see right at the bottom, we have dark blue, 10 to 25 degrees, brown, larger than 80 degrees. The exhaust air has the highest potential, but so has the outgoing air. However, it is more difficult to access it. You need quite a lot of quantities in order to have an economic process, because the effort that goes into it is relatively high. I'm going to come back to this later on. When is this heat created? Is it constant throughout the year, or is it something that is being created mostly in the summer when you need less heat? We have these two flows. We have the outgoing air, which is stronger in summer than in winter, because in winter, heat recovery actually cools down this particular airflow. And we have the outgoing air from cooling facilities, which are also utilized more in the summer because the outside temperatures are higher. So with these two flows, we have about 2/3 in the summer, 1/3 in the winter. For all the other ones, it is relatively balanced, so that really across all the heat flows, you can see a summer emphasis of about 55%, so this is not really a dramatic value. The relevant heat is there in the winter months as well. The same here evaluated by temperature. What do we have available with more than 80 degrees? This would be the brown area here, 70 to 80 degrees. And you can also see the biggest area is 25 to 40 degrees. This is a temperature that can be utilized very well by heat pumps. Here at the bottom area, 10 to 25 degrees. This is when it becomes more difficult to use this heat in a way that is economically feasible. However, some people do, because they say, well, I'm glad to get rid of this heat. I'm glad to sell it to someone. For example, some businesses cool with groundwater, but they're not allowed to heat it to more than 20 degrees. And if they have more heat that is being generated, they have no capacity to do so. So it might be useful then to get rid of this heat and feed it into the heat network. But usually we're talking about 25 degrees plus. This is really the range where it becomes economically interesting. How much do these companies work? What do they actually do? How many hours in a year is this exhaust heat available? This is important to know for operators. So these are all the companies that we looked at. Some of them work more than 8,000 hours a year. On average, it is 7,250 hours. So that means an availability over the year of more than 80%. So the heat really is available pretty much all the time. Only during Christmas week we can see that most businesses have actually, that most people actually close down for that particular week, and then the performance goes down to 30%. So we have to be prepared for that if we work with exhaust air, that there might be some additional backup required during Christmas week. This brings us to our next point. How do we use this heat? How high is the share of the heat that can be utilized? We have two possibilities to start with. Let me actually explain the diagram first. What we see here is a typical heat demand in a heat network. Highest demand during the winter months, January, February, March. Then in summer, we only really need hot water, some commercial exhaust heat, and then the demand goes up again. This is the classic heat demand over the year. What I said earlier, this summer peak that we see of about 55%, this is reflected here in the curve. We have a little more exhaust heat available in the summer than during the winter. So we try to use as much exhaust heat as possible. If we use 100% of this exhaust heat, then the purple curve would have to be here, and the share would actually be quite low if we say we want to use as much exhaust heat as possible within the network with a few peaks, and we would move it down here, then this area that is not being utilized would be enormous. So you have to really find a balance between those two extremes, and this is what we try to do. We try to apply this to all the heat networks in Vorarlberg. So we have about 1,000 gigawatt hours in demand, and about 500 gigawatt hours are covered by exhaust heat from businesses. The rest is covered by biomass and biogas. In this scenario, up to 80% of exhaust heat can be utilized, and we think this is a great use, a great balance actually. There's 50-50 with a biomass on the other side, or another biogenic energy carrier, and only 20% of the exhaust heat actually goes to waste. At this point, we could also think about seasonal storage. If you want to increase your exhaust heat level, you can then increase the purple share, and you could try to move this excess heat from summer into the winter months. This would be seasonal storage. Unfortunately, this is still fairly expensive. We're talking about storage cost of about 10 cents per kilowatt hour with these giga tests that we perform, gigathermal energy storage tests. So it is not really worth it from today's perspective with today's prices to do this. But we think that this is going to be a relevant topic, and it would be advantageous if these fluctuations between the summer and winter months weren't so big. So this brings us back to building, to construction, to passive house construction. So keeping the heat requirements low for the winter months is an extremely relevant principle, because this also lowers the need for seasonal storage. The central technology for utilizing these energy flows, which most of the exhaust heat consists of, are heat pumps. For the non-engineers among you, how does a heat pump work? I'm going to explain it quickly. We have a heat source from which we get the heat, a bit like a fridge where the inside is cold, but it actually releases heat into the environment. We have a compressor, and a cooling agent is introduced into this cycle at a very low pressure. It is vaporized, which means it draws out temperature from the environment, is then compressed within the compressor to quite a high temperature level in order to release the heat that has been produced on this level by liquefying, condensating this cooling agent, and forcing it to release the heat. So the heat is drawn out of the colder medium and fed into a warmer medium. The extent of the efficiency for such a meat pump is called the coefficient of performance, the famous COP. And the closer these two temperatures are between the cool and the warm level, the more efficient the facility is. So the higher the COP is going to be. The COP describes the amount of energy, the amount of heat that I get out for the electricity that I put in. So let's say we have 300 gigawatt hours as a goal, and we feed 100 gigawatt hours into the facility. We have a COP of 3. And this actually constitutes the economic limit. I don't think you should go much lower than that. The higher the COP, the better. So this has a lot to do with temperatures, how efficient these pumps are. This is why I already said if we use exhaust heat at a low level at 20 degrees and use it for 80 or 90 degree heat production, it will be very difficult to do this in a way that is economically feasible because the energy stroke is so high and the efficiency is quite low. What can we do about that? The central element, if we have large energy strokes, we have a cascading of these heat pumps. So we have a heat source with, let's say, 50 degrees. We cool it down to 10 degrees, but not in a single step to help it evaporate. On the other hand, we have the heat medium, which we're also not going to push up in a single step to the temperature that is required, because otherwise the temperature gap would be high. We actually have 4 steps here. We cool down from 50 to 40. We can have the vaporizer at 35 and so on. We sort of do it in steps in this cascade. So overall, we have the individual COPs here, and we have a COP of 4.8, which is actually economically very feasible. So whenever we have medium to high exhaust heat temperatures that we have to cool down, for example, process air, we might consider this sort of cascading approach. What else is important for utilizing large heat pumps? We have the quality degree for heat pumps, which describes how much we actually get out of the pump. For small heat pumps used in households, this would be 50%. For large-scale pumps, the value might be as high as 60 to 70, the quality value. And this is done by efficient cooling agents, ammonia, for instance, or particularly efficient auxiliary systems. To tell the industrial players what they could get for their exhaust heat in gigawatt hours, we have to, of course, also take into account the investment costs, the annuities for the large heat pumps. So we need a few basic calculations in order to do this. And we prepared this in such a way that the investment would be about 600,000 per megawatt, then a lifespan of about 20 years and an interest of 6%. From the point of view of the heat network operator, this is important to know what the initial costs, the initial outlay are going to be, so that he can then go on to pay the industrial players for their exhaust air. We also need an amount for maintenance and for repair work. Depending on the size of the facility, we also need to know what the electricity price is going to be. How much is it going to cost to operate the heat pump? To find out what we can actually charge for the heat. Our benchmark is what biomass costs today, approximately. For example, wood chips, if you burn those, if you can pay the biomass heating, we have a benchmark of about 6 cents until it is paid off. And this is, I think, a good benchmark for industrial players. If this is within their range, then they should feed it into the heat network, because that then makes economic sense. So these are all the basics. If we combine them all together, the results are as follows. We have temperatures of 15 to 30 degrees. This is usually groundwater used for cooling purposes, which is heated and then also refed. We have some free cooling and other cooling facilities, and we have a COP between 3 and 4. This energy is sometimes not used not worth anything, but still companies are glad to be rid of it and can even sell it for about a cent per kilowatt hour. That's not a lot. We continue with temperatures of 30 to 50 degrees, which come from cooling, from process exhaust air, where we have a COP of more than 5. So you can see that here the resale price is a lot higher. For higher temperatures that are used by heat pumps, we have values of up to 3 cents, and any value that is being used directly without a heat pump, we have a price of about 3 to 5 cents that you can charge. Why is that important? Well, because businesses have to be able to get their figures in order. They have to work out whether the investment is worth it for them. Because obviously it is going to cost money to open up these heat sources. What is the risk associated with this? What is the long-term financial outlay? It is important to be able to tell them that. Another result, what actually is the potential? How large is it for the companies that we looked at in relation to their final energy consumption? So we look at how much energy goes into this building, for example, in the form of natural gas, but also of electricity, and how much of this can be utilized. Right at the start, remember at the bottom right corner, this is not usable at all. If we deduct this amount, we have the theoretical potential, which is about 75% on average. 60 to 85% would be the theoretical potential that remains. Then we look at what cannot be used technologically, for example, sludged sewage that just isn't going to exhaust water, that is just not going to work because the facility would just clog up all the time, or the heat in the summer that cannot be utilized. So we deduct 20% for these sort of seasonal fluctuations, and we have a technical potential of about 85%. Next, and I'm going to come back to this later on, what exhaust heat potentials should the company itself use? Rainer said I should actually start with this, but I've moved my presentation around a little bit. Of course, this should actually be the first question. What efficiencies could this use of exhaust heat open up for the company itself? Is there something that could be used especially for decarbonization, for reducing the CO2 footprint of the individual businesses? So this is also something that we need to deduct for decarbonization and for efficiency. And right at the end, we look at what exactly is economically feasible, what can actually be done. So we are now down to 29% on average. For one single business, we had nothing at all remaining, but however, for most of them, there was something that could be used. Like I said, 29% on average, after we removed all the potentials that would not make sense, because they would result in a heat price of more than 6 cents. So we still have this 29%. Looking at the 13 companies that we analyzed, and you can see in the grey shades the individual factors that were deducted for the individual potential steps, and the blue potential is what remains, what can actually be utilized. If we put this in relation to these companies, we have more than 400 gigawatt hours in natural gas. So this alone would make up 32% of the Vorarlberg industrial and trade enterprises. If we extrapolate this 280 gigawatt hours, then we have more than 7 that are actually that can actually be utilized. We cannot do this for one reason. There are some very large companies here that we analyzed, and for them the 29% usability applies, but the smaller the businesses, the harder it becomes to use this exhaust heat on a feasible basis. So here we have a remaining value of 15% for the remainder. And this value of 437 gigawatt hours as available potential for exhaust heat. If you look at this number again from the energy flow diagram, we have an overall heat demand of 4,000 gigawatt hours in Vorarlberg at the moment, and we're going to push this down to 3,000 over the next 15 years or so with refurbishment measures and so on. So these are more than 15% that we can provide with exhaust heat. What is important for utilizing this heat? What do we need to bear in mind in order to bring these two players together, industrial players and heat network operators? For the companies, there is a readiness to invest. There is a readiness to develop the potential that is there. We notice this again and again. Usually the interest in investing in a heat pump is quite low. They think this is something that the heat network operator should do, but they're happy to provide area, to provide space. This is important because otherwise the whole project is doomed. So there is a readiness to cooperate. What they do not want to do is to be obliged to deliver heat. This is always something that is difficult for industrial players, but they are ready to define some framework conditions, some liability regulations for when they cannot deliver, and so on. We actually have negotiations at the moment between at least one of these companies and the heat network operators, so it is taking shape. What do the network operators, what do they need to take into account? They have to bear in mind that there are redundancies. For example, if we have the Christmas period where the heat supply goes down, we need multi-modular networks in order to ensure this redundancy using different heat sources. Also, several companies could be connected into larger heat networks and could then integrate biomass plants where necessary in the system. Large heat storage facilities, this is quite a difficult area at the moment, but it is something that we should bear in mind, I think. What we looked at was the Wärmeschiene Waldau. This is the area between Bluditz and Feldkirch in Vorarlberg, where 3/4 of the industrial exhaust heat in Vorarlberg actually originates from. This is quite a small area, but 75% of the industrial exhaust heat in Vorarlberg is actually produced there. So it would be a great idea to try to cover this particular stretch and maybe think about seasonal heat storage for this particular region. We conducted the study in cooperation with the Vorarlberg University of Applied Sciences. Their part was to find other regions in Europe with similar starting conditions and to look at studies that adopted a top-down approach, so based on a certain number of population or company turnovers or GDP. So working with certain key economic indicators to see how much exhaust heat is actually being produced. They focus on the following studies. There is a comparable European region with a similar industrial structure and quite a large number here, 300 to 800 gigawatt hours of exhaust air. There is also a pan-European study that looks at the whole of Europe with 285 gigawatt hours, but a reference of 25. So the entire exhaust is cooled down to 25 degrees, whereas we cool down all the way to 10. In Styria, there is also a study that actually resulted in the same 437 gigawatt hours, which is a complete coincidence because they had a different reference point, which was 0 degrees, not 10 degrees. But it still shows us that we are moving within the correct numerical parameters. So these top-down studies actually fit in quite well with what we arrived at. So we're moving away from the use of exhaust heat by external players and try to make sure that it is used by the company. Process heat comes in several different temperatures. Quite a lot of industries work with temperatures less than 100 degrees. For example, the metal processing industry, also the food industry. People frequently work with lower temperatures. And this is where heat pumps are always attractive and always make economic sense. It makes sense to replace gas by a heat pump. By now, we have also seen a development in heat pump technologies, so heat pumps that work with low pressure steam up to 140 degrees are at a technological level of 9. So these are really serial products that are ready to use, and they deliver low pressure steam. This is something that is particularly relevant for the food industry, but also for the chemical industry, for drying processes, for paper production. This is where heat pumps are readily available, and we have to make sure that we have a relevant exhaust heat level. But the higher the temperatures that are needed, the higher the exhaust heat temperature is going to be. So in many cases, this actually works really well. Up to 200 degrees, we have a good perspective for high-level heat pumps. I would not use one personally at this point in time, even though they are available at the market. But I think for the future, this is the way to go. For temperatures above that, we're going to need something that burns biomass, for example, or gas for melting processes or other proper high-temperature applications. This is a case example also from the industry in Vorarlberg, a production facility requiring about 80 degrees as its process heat temperature. And we can see here the exhaust heat that is available, anything between 15 and 40 degrees. In the summer, a little more in terms of temperature. All this is available. And looking at these heat flows, we have 29, 30, 40 gigawatt hours that are available as exhaust heat, and 30 are being consumed. Required are slightly more than 22 gigawatt hours. So we have a lot more exhaust heat available than we would actually need for production. We can pick out the most economical flows, and these are the ones with the highest temperatures. This is what we did for this particular company, and we looked at 3 heat sources in particular. The blue area here refers to cool temperatures, so anything that that refers to heat being drawn out from the production processes. Then we have wastewater leaving the company in large quantities with up to 30 degrees, and here we have the outgoing air. This is 600,000 cubic meters per hour that are used here in order for ventilation. And we only used a small part of this. It is quite clear that we have a lower number available in the summer, but it is still the largest energy flow even in January. This is really what we're taking out of the exhaust air after it has already been through the heat recovery process. So we are not going towards 70-80% here. Usually we're staying below 50%, sometimes up to 60% if we're in a particularly fortuitous scenario. If we use this and we compare it to natural gas use, which is also higher in winter than in the summer, we can see on average that we are able to cover the requirements even in January. Here a peak load coverage of about 2% that is required on top, not a lot. So this would be a step towards a CO2 reduction for this company, full decarbonization really. We could also deliver up to 15 gigawatt hours into a heat network. This would be particularly good in the summer. We have a basic load here that is actually very good, and we are currently negotiating with a heat network operator. And it looks as if we are going to be able to come up with a solution where the peak load coverage is not going to be covered by gas, but by a network operator, because we don't actually need more than 80 degrees. So they might deliver 1 gigawatt hour from biomass in winter and will receive 3 hours of exhaust heat in the summer. What exactly the ratio is going to be is not determined as yet. We're going to find out over the next few weeks. Like I said, negotiations are ongoing, but it looks as if we're going to be able to leave out the natural gas share completely here. We're going to be able to cover even the peak loads with biomass, and we're also going to save a lot of energy because of this heat recovery. So this, for me, would be a great example for decarbonization and still feed some exhaust heat into the network. Another case study here to conclude. We have different heat sources, cold buffers, wastewater. They are all being fed into the system. This is what the heat pump looks like. This is the evaporator drawing the heat out from the buffer. We have a two-layer compression here because the stroke is quite high. As you can see, this works, but you do need two compressors, and we have one high temperature buffer and one low temperature buffer that are being loaded sequentially. If you need only 80 degrees, it would be more difficult to stay economically feasible. We still have about 25% of the overall demand, which is low temperature exhaust air, which makes the whole thing a lot more interesting. And this is also something that we have to be aware of. Let me give you an overview of the economic feasibility. Let's just look at one column. Maybe this is a low energy price scenario. So this is the one that the cursor is in right now. So the heat pump is operated with electricity 10 cents per kilowatt hour and gas only 4 cents per kilowatt hour. So this is something where the industrial players say, okay, this is a ratio that is pretty good. If the prices remain low, then we can go ahead. Then we look at what exactly is the energy demand, what is the electricity cost, what is the gas cost and the usage, of course, what are the investment costs, how can we amortize the investment. 20 years would be the amortization period here. Then we have the maintenance cost, the repair costs. As you can see, with the low energy price scenario, the heat pump, including the investment cost and the initial outlay, actually achieves a better result than gas, a better heat production cost from the very start. And of course, the higher the energy cost, the bigger the discrepancy. Of course, industrial players know where the CO2 tax could possibly go in future, and they are trying to take this into account. They do say, well, we have to be aware of the fact that gas might be costing 6 or 8 cents at some point in the future, and then electricity prices are going to go up. But if this is something that we can take into account in the individual scenarios, this economic feasibility, I think it is something that increases trust on the part of the client, and it shows them that we're being transparent and honest. So this is what we are trying to do at the moment with this first one of the Vorarlberg top 10 users of the Vorarlberg industrial players, and we really hope that this is going to be implemented. How is this study transferable to other regions? Especially given the fact that Vorarlberg is not a heavy industry region. We are industrialized, but we don't have heavy industry that needs a lot of raw materials and a lot of energy. We have about 5,000 kilowatt hours per person per year. This is comparable to Switzerland, also comparable to the rest of Austria, and also comparable to the European average. It might, however, be twice as much depending on the region. So with this exhaust heat potential, you could actually enter into political discussions also in other regions, because it is very likely that energy usage in other regions are larger. This brings me to the end of my presentation. For more information, please check out the links at the end of the presentation that you can see here. Take a look, and thank you for your attention.